Alright, in this unit we are going to return to some more of our true geometry topics, but some of the algebra skills we've been working on are really important. So we're going to do a quick review of radicals before we get into the trig topics. So one of the things that's important in trig is being able to handle radicals as exact answers, because most of our answers need to be exact. So you need to leave the radicals in and not go out to some yucky 7-place decimal. So we're just going to take a quick reminder that when we are faced with a radical such as the square root of 112, we are looking for what perfect squares are in 112. So one of the easiest ways to do that is to just go ahead and make a factor tree. And as I list the factors, I circle when I get to prime factors or a perfect square. So what I really have here is I have two 2's, I have a 2 squared, I have a 7, and I have a 4. So I haven't changed the value of 112, I've just rewritten it in a form I can use. So then I go through and I say, well, what's the square root of 2 squared? That's 2. Can I take the square root of 7? No, so that stays under. The square root of 4 is 2, that comes out front being multiplied, and so this answer is 4 square roots of 7. That is the exact answer, completely simplified. So that's the sort of work you need to do when you're handling radicals with trig. If we look at the next example, 5 times the square root of 45, 45 has a perfect square of 9 in it, and so this 5 from out front, the square root of 9 is 3, leave the square root of 5 under, I have 15 square roots of 5. Now when I'm faced with a fraction, I have a couple of choices. If both the numerator and the denominator are under the radical, I can simplify this fraction first. And so I know that these both have a common factor of 8. And so when I take that out, I have 3 over 10. Now we remember from our expressions unit, it's bad math grammar to leave a radical in the denominator. So by our rules, that square root of a fraction, I can take the square root of the numerator over the square root of the denominator. Then I have to go through that process of rationalizing the denominator, of multiplying the numerator and denominator by that value. Like radicals, you can just multiply them. The square root of 10 times the square root of 10, square root of 100, which is 10. There are no perfect squares in 30, and so that is my final answer. Couple of different ways to look at D. We could go ahead and rationalize the denominator if we want, but I could also think about the fact that 24, the square root of 24 would be the square root of 8 times the square root of 3 over 2 square roots of 3. And square root of 3 divided by the square root of 3 cancels. Now 8 still has a perfect square in it because 8 is 4 times 2. So 8 becomes 2 square roots of 2 over 2. And then those 2's cancel, and I'm left with the square root of 2. Now you could go ahead and rationalize the denominator, multiply top and bottom by 3. You're just going to have more canceling to do, but you will end up with the same answer. Now distributive property with radicals, like parts get multiplied. So I have the square root of 5 times 15 plus this whole number out front becomes a coefficient, 3 times the square root of 5. Now I don't multiply these usual because I like to factor them. So I have 2 5's, I have 5 squared. So the square root of 5 squared is 5 with a leftover square root of 3 plus 3 square roots of 5. And remember, unless these radicals are identical, we cannot combine them. So that is your lowest term answer. Continue with some quick reminders. These radicals are exactly the same. So if I have 1 square root of 5 plus 4 square roots of 5, I have 5 square roots of 5, so those can be combined. But if I have the square root of 3 and a square root of 5, I cannot combine them. That answer is in lowest terms. When I face something like example C, in 5 square roots of 7 plus the square root of 63, initially you might think you can't do anything, but 63 is 9 times 7. That's not in lowest terms yet. So when I do put it in lowest terms, the square root of 9 is 3, the square root of 7 is left over. Now I have like radicals, and so I have 8 square roots of 7. When you multiply radicals, you can combine them. Now this is where I don't necessarily like to multiply 18 by 6 just to factor. So I'm going to go ahead and factor 18 because I know it factors into 6 times 3. So really what I have is 6 times 6 times 3 if I were going to multiply these together. This is a perfect square, so the square root of 6 squared is 6 square roots of 3. Again, if you multiply 6 times 18 and factor it, you will get to the same place. I just like to take shortcuts when I can. When you think about variables, I always write them as groups of 2, as squared groups, because that's what we're looking for. The square root of k squared is k. I can't take the square root of k, and so I'm left with k times the square root of k. Now this last one, we are back to needing to rationalize and or cancel. So a couple of different things that you can look at. You could simplify these first. So I see this as 4 times the square root of 9 times 3, and 48 is the square root of 16 times 3, because I happen to know that there's a perfect square of 16 in there. And if I clean that up, I have 4 times 3 square roots of 3 over 4 square roots of 3. And this works out nicely for me because the square root of 3 and the square root of 3 cancel, 4 and 4 cancel, and that leaves 3. Just a couple of quick practice problems on rationalizing the denominator. Most of your denominators in trig are going to be square roots of 2, square roots of 3, square roots of 5, and so the rationalizing is pretty small numbers. So this is what cannot stay, so we multiply top and bottom by the square root of 2. So this becomes the square root of 2 over 2. Nothing can be canceled. That's lowest terms. Here my denominator is the square root of 3. So it's the square root of 3 over the square root of 3 this time to rationalize. Now remember, this number right here is essentially 1. So I'm not changing the value of my fraction. I'm just changing its format, much like when we reduced fractions or when we make common denominators in order to add. So numerator times numerator, 5 square roots of 3. The square root of 3 times the square root of 3 is the square root of 9, which is 3. You will always get a whole number, non-radical, in the denominator. That's the whole point of doing this. 5 and 3 don't have anything in common. Radical 3 and regular 3 do not cancel because radical 3 is 1 point something as a value. So it does not cancel with 3. It is its own number. So that is in lowest terms. Here, my denominator is the square root of 5. So the whole number doesn't have another whole number, so that's just 3. 2 times 5 is the square root of 10. The square root of 5 times the square root of 5 is 5. 3 and 5 do not have anything in common. 10 does not have any perfect squares, so I'm in lowest terms. Now D, you can do in two different ways. You can either rationalize by multiplying top and bottom by the square root of 3, or you could see that 6, square root of 6, could be rewritten as the square root of 2 times the square root of 3. That's over 3 square roots of 3. So these square roots cancel, and my simplified answer is 2 square roots of 2 over 3. So that is all review. Try the next couple of quiz practice problems and then tune into section 2 video.